Okay, so maybe a little recap of few of you, but we'll just start with what is machine learning here. Okay, so now, okay, so few of you are from different stages of learning, right? Okay, and so let's see it independently. So what is machine learning? That is the first question. Okay, and let's compare it with the traditional programming. Okay, it's like all of you already know, but in traditional program, what do? You write the code, the logic, right? You actually write the logic over there in traditional program. Like, if to handle some customer situation, if to handle some condition, you write the logic. Okay, if there is some new situation that has to be handled, you create a team, you create a time, and you handle it. So happens. But that sort of actually traditional programming suffers from this problem of continuous maintenance. Right? If there is something new, you have to add some functionality to the program. Right? This is where machine learning comes into action. Machine learning means once you're not creating a logic, right? You are actually we should have sit downstairs today. That is empty.
From next class onwards, shall we wait?
Yeah, no, we can downstairs.
I think better if you can shift.
Yeah, I think this is all. There's nobody else coming, I guess. Can you close the door? Huh? Hmm? So that's what we initially needed. We're trying to create the logic. Okay, this is the important way. So in the first program that we'll see today, we'll see the application creating the logic for you. Okay, this is the hypothesis for you. Okay, the application, I mean the machine learning application that you're creating that will generate the logic. That's the whole point around it. Okay, so now, and what is the applications of it? Machine learning is a very integral part of AI. Okay, in artificial intelligence. So first point, when artificial intelligence really started, it had really nothing to do with machine learning. There was no machine learning component in it. Okay, it is over a period of time that machine learning got added to your AI. Okay, so with machine learning, what happens? So you can answer a question. That means if you have a machine learning application, it can tell you what will be the sales, what will be the metrological report. It can do all these things. It can give some insight about the data, right? What is this data about? Like this is where people use machine learning for data mining, right? You might be actually in the course you already have data mining course.
Mm-hmm.
That is like using machine learning like algorithms to tell what is there in the data. Then you have, mind augmented decision making. A lot of people use machine learning to create dashboards. I mean, from the data, you create some analysis. From analysis, you create some dashboards that can help in decision making. Like you want to start a new Manipal's hospital, which is the best location, where you can get doctors at reasonable rates and more number of patients. Broadly, machine learning is divided into three categories. Okay, one is your supervised machine learning, one is unsupervised machine learning, one is reinforced machine learning. Okay, online machine learning. So you need to categorize that. What is the idea of supervised machine learning? How did you learn identifying a cat versus dog? When you're a kid, right? Your parents or grandparents showed you a cat and basically told you this is a cat, isn't it? Okay, so that is basically you saw, they told you this, they told you, but they didn't tell you this is the tail, this will be the hair, and all those details nobody told you. But you created that logic in your brain, right? So somebody gave you examples and you generating, mapping it based on the examples. Okay, this is your supervised machine learning. So other examples are like yesterday we were dealing with housing data. We have dealt with different type of data, or many data where you have how, like maybe I can show that. This was your housing data, isn't it? This was your housing data. Now here you see you have square footage, floor, total floor, bedroom, living room, bathroom, price. Okay, that's not useful now. So all these things you have. So supervised means you have this data till bathroom and you're predicting price. So when you want to create a logic where you first will give you you'll give all the details, square footage, all these things, as well as price. You'll tell if a house has this much, this is the properties, this is the house. If a house has this is the property, this is the house. After some point of time, when you are sufficiently trained, it will give only if this is the house price, tell me how much is the price. This is supervised machine learning.
So how will you predict the price?
Huh?
How will you predict?
This is where your algorithms comes into picture.
Oh.
Okay, this is where we'll do that today. Okay, so there are a few terms we should be very comfortable here. Okay, because if you are, I highly encourage to read. There are some good books. Okay, so please, I'll refer them. So you can read that. Maybe initially you'll find it a little difficult because the expectation is a little higher when for whom they expect people to read it. But what will happen during this course, right? We'll be talking something similar on similar terms. So, a lot of those terms will become clear. The most important aspect where I found, people becoming little, because they have a lot of notation here, syntax notation. I would like to clear that during the entire trip. Some syntax notation, just keep a mental note or you note it down somewhere so that when you're reading the book, that notation comes and this is what it means. Okay, so if you see in this diagram, there is something known as feature data. Okay, in this example, feature data will be, feature data will be a vector. Okay, what is feature data in feature data is this information. Okay, a vector of this. Got it, right? I mean, for you guys, yesterday we discussed vector. Okay, vector is to represent a feature. Right, in NumPy we have created a vector, right? Okay, and that is representing this feature. So it is like 1, 1, 7, and whatever is it, comma, all this thing consider feature data. Feature data in supervised algorithm means the data which is, which is like independent variables. This feature data is also known as independent variables. This is not dependent on anything. Whereas the target data, this is feature data, is also known as independent variables. Independent. Then you have target data. Okay, target data is in this case house prices, right? Right, like 62,000. Next house prices, whatever it is, 78,000. Understood, right? This is target data is also known as dependent variable. And remember the term, all these columns are also known as variables. Okay, I'm saying dependent variable and independent variable, but collectively they are known as variables. Okay, variables. Okay, because different book follows different terminology. Okay, variables.
Target data can be more than one point, right?
Target data. If you are using one machine learning algorithm, as of now, target data is one. Okay, target data can be more in case of deep learning algorithms. Okay, in all this case, it will be only one. Got it? Okay, so sometimes the feature data is also known as explanatory variables. Explanatory variables. Okay, just another name here. Okay, we have feature data. Okay, we have target data. We have independent variable. We have dependent variable, and target data is dependent variable, also known as response variable. This is a response to that. Okay, response. Okay. Okay, this is what happens in supervised. In supervised algorithm, you have feature data, you have target data. Okay, as you can see, one thing, the target data that you see here, is it discrete or continuous? Hey, what is discrete? Discrete means continuous. Yeah, discrete means fixed values. Like you know how what are the possible values? Like 1, 2, 3 is limited. Okay, like discrete values can be like yes or no. Discrete value can be discrete value can be classes like entertainment, politics, sports, limited stuffs. Okay, that is your discrete variable. This is continuous here. So when in a supervised algorithm, when the target is continuous, it is known as regression. When target is discrete, it is classification. Okay. Okay, so give me some more example of regression problems. Like house price is a regression problem. Sales is a regression problem. Okay, then
Rainfall is
a regression problem. Then self-driven cars, you might have heard about, right? Autonomous cars and self-driven cars. There, that is a regression problem actually, because all you do have to find out at what degree you have to change the steering wheel. That is a regression.
So hospital data that comes as a discrete.
Number of days patients will be there.
Yeah.
That is a regression problem. Number of days patients will be there, predicting the number of days patients will be there in the hospital. That is a regression problem.
So the type of diseases, that is a classification. Diseases.
Right. Based on the medical report, if you are predicting which disease the patient is suffering from, that is a classification.
Airline, again, it's a regression.
Airline, how much
Flights,
delay will be regression? Yeah. Delay or not delay is a
Classification.
Right? Can you guys give me more examples?
person buying a movie. Yes or no, maybe.
Person buying a movie.
Looking the trend.
Right. If person will be clicking the ad or not. Yes. That is the case of classification. Right.
Getting more likes or dislikes for a particular content in YouTube.
Number of likes, indeed. That is a
classification. Like or no like.
Yeah.
Number of likes. Number of likes.
Number of likes is
regression, but yes, like or no like, it's classification.
Yeah. Okay, so I think everybody understands what is regression and classification now. Okay, so now
Sometimes we generate future based on the input, right? So that is again called like a future data or some any other term is there. If you are generating some new future out of the data, some combination or something like that.
new feature.
Features.
New feature out of the data. That depends on the data type. If the data type is continuous, then you can say it's a regression problem. Like you're talking about, in internet data, age is missing, you're generating age. That is your regression problem.
No, you
No, I'm
say
asking-
he's not saying that. He's saying a new feature altogether. Like, okay, now he has found out something different. I don't know if it's possible.
I mean,
You mean like the outcome type of the
No,
outcome?
within input itself. It's
We
like
created
by
a column.
combination of something I'm generating some new future.
Something like, okay, on the graph you have X and Y. He's finding out Z, basically. Based on the graph.
It's like that is personal. If you have some data taking about lurking variable, then it is fine. We'll find a variable which will actually more bias the output. But if you are saying like from the existing variable, you extract something new, how would this is possible? Because we are predicting something with the known ones, not the things that are never. If it is lurking, then we'll create that variable. We'll create a data pipeline and get that, and then try to do something.
when you talk about, generating features, there can be, few things can be done is, you can generate features from existing features. Like you have income and, age bracket and you're predicting tax. It's not really predicting, just deriving values. This is one thing that is possible. But if you're, okay, so what is, and another thing, for example, you have, okay, so you have some data, and from that data you are predicting whether the customer will leave or not leave. I mean, it's like, you really don't have that in churn data. Sort of, this is known as churn data. Okay, do you want to predict the customer will leave the organization or not? Got it, right? So in that case, you don't have direct output column of churn or not. You derive it from the existing data. So basically, it's mostly derivation.
Yeah.
Okay, it's not really prediction in that case. Okay,
So that is also part of the feature.
that now your feature list increases. That's it. Okay, so we'll do some things around it. So I think if you have some doubts, it will become clear. Then you have this is category of supervised, right? Then you have unsupervised. In unsupervised, what happened? You only have feature data. There is no target data. Okay, no target data. Okay, so only feature data, no target data. That means you have the data, like you have housing data. It's not that you do not have target column, but you won't be telling it is a target column. Okay, generally feature data is represented by this notation, X. Capital X, right? Okay, and ith row of this is represented by xi. Actually, it's a small xi. Got it, right? So this is the feature data. And what happens in case of unsupervised, you have the housing price is also there, but you won't be breaking that up into feature data and target. The entire data will be feature data only. Okay, So what you do in an unsupervised algorithm, you try to find, you try to do clustering. Like, you try to find similar, houses. Yeah, you find a similar, you have to find a pattern in the data. You have customer data and to find what is the best way to divide the data into, right? If a user is buying this product, what should be the best product that can be recommended to that?
So in the housing example, like how do we divide? Is it by square feet or bedrooms, number of bedrooms? How
What
do
you
we
do?
cluster?
Yeah, so in basic words, we'll discuss that, but how do you cluster is each house can be represented as a vector, right?
Yeah.
And vector consists of pricing, square footage, and many other things, right? So what is this? If now is that point where I would want you to imagine something. This is a vector, right? If you say there is a vector of 2 points, 5 or maybe 3 points, 5, 3, 2. Can you imagine this point in a 3D space? Very easily. So from X it will be 5 distance, from Y it will be, and from Z it will be 2, whatever it is. Right? This is what you imagine. Now can you imagine a 8-dimension vector in a 8-dimension space?
8-dimension.
Because that's what is there in housing data is just assume 8 columns, including pies, 8 columns.
Difficult.
Of course, you cannot imagine. We have only capability of imagine 3-dimensional. But the same way you can imagine this as a point in a 3-dimension space, you can extrapolate that a 8-dimension vector to be in 3-dimensional space, in an 8-dimensional space, right? Extrapolate that. So you can imagine that when this is so that's what it is. What a machine learning does. Each data is nothing but a vector in n-dimensional space. Is it clear?
Yeah.
This is what you should understand. This line is the most important line in machine learning to understand. Once you understand this line, the rest of the stuff you can connect from here. Okay. So what you can see, if you are representing all the data, can you imagine your data to be represented like this in n-dimensional space? Right? Okay. This is what the technical term for this is each data is represented in a hyperplane. Okay, this is what typically it means. Is it clear? Now, okay. Now, what you're trying to do clustering means there can be many ways. I'll tell you the simplest way. If this data is closer to this data, then you can tell, right, this belongs to one cluster. We'll discuss many other ways. Now, a lot of problems become simple actually. If you want to find a data which is very different from all the other data, that will be very far from all the data, right? Okay, this is known as outliers. There are a lot of techniques which tries to. So what is this? The next term that I'll introduce here is vector distance. You remember when you discussed broadcasting, we discussed about how to find difference between points.
Yes.
Broadcasting. So if you find the distance between this point and this point versus this point and this point, you realize this is very far away, right? So the vector distance of this point from the entire lot is very far. So that's why this is known as outlier, right? All the answers, as you learn, you'll give more precise answer. But with this thing in imagination, like you can basically give a high level answer to all the questions. At least you will start correcting. Okay, so that's the part.
Sir, it's like regarding that unsupervised learning, one of the example what read that is how Google News actually try to cluster different news sources. How actually it works? Like almost all the sources is having some common content. For an example, Narendra Modi. It will be like they'll have common content on Narendra Modi, whatever is going on in the media. But how they classify
Some keywords maybe.
That's what I'm interested to know.
Some keywords which are content on the Modi.
That's fine, but
No, but what Google News does it divides the data into politics, sports, okay, economy. It divides the data into that. Okay. For that, what it does is anyway, text data is not understood by machine learning.
Yeah.
Okay. We learn that how to convert text into numbers. Okay. Once you convert the text data into numbers, what happens? It tries to find so once you have converted text data into numbers, each text data converts to a vector, isn't it? Right? So maybe, considering you have 200 words, each text data is a vector of 200 words, 200 elements. Is it clear? Now, you will just plot, without explaining a lot of stuff, you can imagine these 200 points. I mean, this point, which is in 200 dimension space. Okay. This point, you have to find what are similar, which are the points which are closer to each other. That's all. Got it, right? Okay.
It's a little more complex than the supervised one.
No, not complex as such. Okay, I mean, this is a very simple problem, just that we haven't discussed those things, that's right. So finding points, I mean, these are not clustering techniques. I just gave you without explaining any of the algorithm, but fundamentally what you do in n-dimensional space, what are the closer points? Just understand that. Just a masala question here. Okay, so suppose in case of classification, you have all the feature data, right?
Yeah.
And this feature data is of type, say, A, right? You have a new point, okay, and this feature data is of type A. This feature data is of type B. Without explaining any machine learning, let me ask you this. And of course, this is type C, this is type C, this is type D. So now suppose you have a new point for which you have to find which type is it, and it falls here. What will be the type? That's right. This is nearest neighbor algorithm. We haven't discussed. So you're telling by yourself, right? So that's what. If you have the right foundations, a lot of things, even if you don't know, you can extrapolate. Trust on this. Okay, so build the foundations very solid. That's all. You might not know a lot of things. Okay, like in most of the whatever domain you're working, you might not know. But what has happened is you build a solid foundations. For the things you don't know, you can actually extrapolate. Build that skills. Okay. Okay, so now this is the journey of the simple data scientists. Okay, we do data gathering, data cleaning, data processing, data visualization. Okay, after getting the data, this part is one of the most challenging stuff, data gathering. Okay, and data cleaning, data processing.
Everything is done by data scientists. Then what others like data analysts and data engineers?
Those are, I mean, this is generic term. So some companies now companies have started giving away this title of data scientist. Earlier it was not the case. So earlier, in fact, it was software engineer.
So is it something like data analyst will do steps from data gathering to data visualization, and then from there on?
Theoretically, yes. Practically, no. Okay.
Big data also comes into picture.
Yeah, big data comes into here. This part, or after doing this part, after this part, when you've done everything, cleaning and all that, then you use big data to model the data and store it. Okay. So yes, but a lot of, this is the work that we have been doing. A lot of ETL folks and all that, right? They have been in this sort of work, data gathering to data processing and storage. Okay. Okay, and after visualization, that means visualization means you really understood the data, or you are really capable of explaining the data. Once that phase is ready, you can do machine learning, and in machine learning you have both supervised and unsupervised. Unsupervised, you have clustering association, which we discuss. Supervised regression classification, then basically finding which is the best option among them, right? So without beating a lot of bush, let me get to some important concepts. Okay, remember this diagram that we have it here. You will be very soon needing it. Okay, this is like for a given problem, how do you start solving it?
What is this?
Yeah, for a given problem, you have to identify it is a classification problem or a regression problem. If it is a classification problem, there are a lot of techniques here. For a regression problem, there are a lot of techniques here. When do you use what? Cheat sheet. Okay, of course, there you can find more such cheat sheet. Of course, I'm not the creator of this. This is done by Scikit-learn itself. There are a lot of people who has created nice fancy cheat sheet. If you Google, you'll find that, and that won't make sense now. And don't try to read that now. When you have touched a lot of algorithms, and you'll naturally come up with this question that now that I know all these things, when do I apply what? So some of those answers in a high level can be found there. Okay, though we'll discuss a lot of other things. Okay, so a little a recap on the calculus part before I get into this. Okay, oh sorry, and before that I have discussed. So first thing that we'll discuss is linear regression. I will not really discuss the maths part now. Okay, we'll first discuss what it is and why you should be doing it. Without explaining a lot of internal literature, and first explain the overview of it, and I'll go there. You can see this house price data, right? Okay, so I'll simplify this. Just imagine for a moment so this is size, square footage. You can imagine as 100, 200, 10,000, 8,000, 2,000, and something around 5,000. And this is price. Right?
Yeah.
And you have select from the data that you have seen earlier. You have selected two columns. One is price, one is house, one is size, and you try to plot it over here. Understood, right? This is like you're simplifying the data. Okay, so this is say your different houses getting plotted. Now, what you have to do, you have to, I mean, this is the training data. That means you have the size of the house, price of the house, and what you have to do is you have to find the best formula, best logic. Using that, you can predict the future. Given the price of the house in the future, you want to predict the size of the house. You want to predict the price of the house. That's it, right? Okay. So, what we using linear regression, what we try to do here is, so basically we'll call it simple linear regression. Right, simple linear regression. And this for explaining linear regression, this type of example you will find in every book. Okay, and this is where it started. So people continue to use this example as a legacy also. Okay, so this is a very standard example to explain this. So what we will discuss now, simple linear regression. What we are trying to do in simple linear regression is we are trying to predict a straight line. Okay, which would give you the relationship between the feature data and target data. So my first question is, what is the feature data here?
Is the size of the
right? It is a, okay, or you can represent by this. This is only the square foot information. What is the target data here? Yeah, whatever I'm writing here, as soon as you increase more features, you can change the vector size. That's it. Right. So y, what is the property of y? Y is continuous, right? So we'll write it like this: y belongs to R. The real data. Okay, that's what it is. This is feature data. This is target data. Now, what you want to do in simple linear regression, predict a straight line. Okay, which can best depict the relationship between the feature data and target data. That's what linear regression. So this is linear regression means it is for, okay, let's predict a straight line for finding the relationship between feature and target data, right? So how do you represent the formula of a straight line? This is the simplest case, no? Right. Is it clear to everybody? What is y? Y, see, what is m and c? M is slope of a line. Okay. So given a line, okay, m is the slope of it. How is m calculated?
Y2 minus y1 by y2 minus x1.
Okay, that's cool.
That is the change over y-axis by change over
right.
x-axis.
So assuming your, right. So this is the y. Understood, right? This is y2, this is y1, and this is x1, this is x2. Okay, so it is y2 minus y1 divided by x2 minus x1 is equal to, you'll this delta y by delta x, right? This is your slope. And what is your c? C is the intercept where it is intersecting this axis, right? That is how you represent a line. So given a combination of slope and intercept, you can have how many lines? I mean, infinite lines, right? I mean, multiple combination, right? You have infinite possibilities of M and C. So each line can be uniquely represented by these two properties, right? So what are the how many such possibilities are there? Infinite. But what do we have to do? We have to find the best line. Okay. So the best line will be something that
the distance between the predicted point and the line.
absolutely. So among all these lines, okay, what will be the best line? Best line will be the line from which, so how do you, once you have predicted the line, let's say, let's say among all this line, you have predicted this line. Okay, just as you know, as of now, just theoretically assume it, you have predicted this line. We'll discuss here. So what will happen from, you have to, there is something known as cost. Okay, so what will, for this chosen line, or for any line, what will be the cost? The cost will be, okay, for each of the point, the actual cost, or the for each of the point. For example, you have this point you are taking into consideration now, right? For this point, what will be your, so this will be your x, sorry, this will be your x and this will be your y, isn't it? Okay, this will be the predicted, sorry, this will be the predicted y, and this will be the value of x. Is that clear to everybody?
Yeah.
But what is the actual y? This one, right? This is the actual y. So I can represent by not y cap. Y cap will be represented for predicted, y will be for actual. Okay, so cost will be y minus y cap, the difference between the actual value and the predicted value. Then you are doing a square of it. Okay, square of it so that you get rid of the negative notation. Also, you basically, if it is very less, if you are doing a square of very less number, it becomes further insignificant, right? Okay, so that's the reason you do square, and you will do this operation for all the lines.
Yeah.
Okay,
All the samples.
all the samples, and after that, I mean, you would do, I mean, after you have calculated this, you do a square root of it. Okay. Okay, so this is equivalent to, I mean, mathematically this is equivalent to 1 by m got it, right? Square root is equivalent to this. That's precisely because when these things were discovered, right, 30 years, 40 years
This is
back.
root mean square.
This is root mean square error, right? Okay, this thing was discovered like at that point of time, 30 years back. Around that time, doing a square root was a difficult job. So they found out, you know, this is historical. That's why it happened. When it proves well, I mean, it works out well for all the questions. So that's why nobody tried to. Understood? This is your cost function, right? So for all the points, remember, this will be calculated for all the points. See, for each line, okay, so you can see cost is calculated for each of the points. Is it clear? For each line. So which line will be chosen?
The least cost.
The least cost. Right, that will be the chosen line. And given the cost, okay, so next point. Okay, so who does it? This is done by your gradient descent. Given the cost, it's really not that. How many possible lines are there? Infinite. You cannot find infinite lines and see the cost. You have to find the optimized way to find the line which has the least cost, isn't it? So this is done by your gradient descent. Gradient given, what does gradient descent do? Gradient descent from the log cost, it actually computes the best line. Okay, that is gradient descent. Gradient descent uses cost and computes the best line.
Why should you take the least cost? Least cost.
Least cost means it is closest to most of the lines, isn't it?
If you have least cost, that means there is a line very close to the line, so that cost is minimum.
Okay, so basically gradient, okay, got it, right? You will choose the line. I mean, basically the line that will be chosen will have the least cost. Okay, and gradient descent does that. Uses cost to find the best line.
So for one particular line, we are calculating cost for all the points, right? And then, like we just were doing for each line. So
each line.
Sum of all the cost. Then
no, not sum of all the cost. For each line, you have cost is for each point you are calculating, right? Each point per line.
Yes.
Okay, so which line is chosen? The line with least cost.
But there are so many points, right? So overall, how will it determine, like sum of all the costs for each point for a particular line?
No. Cost is for each line. So you can see what I'm doing is sigma. This is for each point you are calculating this, right? And you are summing it up for each line. So you will just compute it among all the lines.
Okay.
Got it, right? You're competing for all the lines, not all the points. Okay, for each line you're calculating using all the points, and then you're doing the comparison.
Okay, this is for each line for all the points.
Yeah, right.
So this gradient descent is applicable for this particular algorithm, or in other algorithms also we use gradient descent?
No, gradient descent is very important. It is used in neural networks also. This deep learning also, I think, yeah, it gets used. Okay, so I will discuss the gradient maths around gradient descent, but first you got a picture around it, right? Now let's see some code. Okay, how it works. So this is scalar data sets has a lot of inbuilt data. We are using some regression. We are generating some regression data out of here. Okay, if you see what is generated now, x, I'm given x is equal to, this is very useful when you are learning actually. X, if you see, x is C1 values. This is the value of x.
It's one variable.
One column, right? One column. This is x data has only one column now. Since you're given here, number of features is equal to 1. Then,
But I can generate that by random also.
huh?
I can generate that by random also.
Random also, but it is inbuilt library.
Okay.
Okay. So, and this is your y, this is your output. Got it, right? X and y. So I will plot it first. Okay. So I think few of you haven't done plotting, but a very simple plot. Import.
So is the recording is on?
Recording. So today I'll be Devi Prasad. Today I'll be sharing all the recording and everything. Okay.
Okay, I want the last 2 classes recording I made.
Right. I'll do that. I'll do that. No?
Friday, Saturday, and today.
Friday, Saturday, and today. Okay. This is not working, or how is it? It's not showing anything. You see, this is the points. Understood? Right? It's not really the straight line, but this is the points. Okay. So what would be the line? The line would be something in this direction, isn't it? Right. So we want to really see if it can create a line in this direction and plot that also.
The intercept is 0.
Huh?
Intercept is 0.
The intercept should be not 0 actually. 0 is here, right? It is
Okay, it's
minus 180 sort of.
Yeah.
And if you see the slope, what should we, so yeah, intercept we can see from the diagram and see it should be minus 170 something, right? And what would be the slope?
Slope is positive.
It's one only.
It's positive. So let's see, like, you know, this guy and this guy is there, and we can plot it something like, you know, 50 slope should be there, right? That's the whole drill. Okay, let's see if our algorithm can
Why
calculate.
will the slope be 50?
Slope will be 50.
The values are
No,
different.
slope is the one which intersects the y-axis, right? The line. The line, let's say.
Yeah, see.
Go to 100,
Oh,
we are getting different values.
Time is different in color. Increase noise. Noise you could take.
Color is white.
Oh shit. Okay. Right. See, that's what is happening. Should be, you know, the delta, here the delta y is how much?
50.
Right. Here y2 minus y1, x2 minus x1 equal to 100 minus 50 by 2 minus 1. So as we see from the diagram, the best line would something be close to 50, not necessarily 50. Okay, and M and C would be close to minus 170 sort of a thing. It should be 50 sort of a thing.
Yeah.
Let's see if linear, this is what we see from the diagram. Of course, 2 dimensions we can see. Beyond it, we cannot do that also. What we want linear regression to return us something like this. Okay, import linear model Scalar or model import.
So, what is that noise? Specified
Oh, noise is how much far it is from the. If I mention noise is equal to 0, all the data will be the same line, straight line. I added a noise so that to create it very simple to a realistic situation.
The SQL is kind of inbuilt library which has all the model and the data sets.
Right. Scalar is a scikit-learn library. Okay, it has all the libraries, all the machine learning algorithms, all the data set. It's a very rich library. Okay.
It's part of Anaconda.
It's part of Anaconda. You don't have to install it. Okay, so what I'm doing, this line is like creating an empty brain. Okay, empty brain. It's like telling it you have to create a straight line, but we haven't given it any data. all the data you will be giving it, you will be using fit function. Right? When you do fit function, it is like, giving the data. Okay. Now, understood what is fit function? Fit is like training the model, training the empty brain. And if you want to see here, it's pretty close to 50, isn't it? 45. This is the slope that it has calculated. Okay. This is the intercept, minus 42. Hey.
Then the intercept is different. It's like minus.
Okay, it is telling for 0 where it is intercepting. Y-axis is 0. That's what the intercept will tell, right? The intercept is that y equal to 0, and what is the x equal to 0, what is the y value?
Yeah, we have already fed the data. So if we have fed the data, then it's understood.
Okay, if you calculate for the x equal to 0, there what is the intercept?
But it can't change. Intercept you can't change. For a line,
Let me plot it. Okay, just let me say that. So for LR, you have this predict function. Predict means it will give an x, right? I mean, after you have trained the model, right? It will give the x and it will give you the prediction. Let's see what happened over there.
you
Okay.
can choose 50.
Huh?
You can choose 50.
50 what?
I mean, you have to assign the value of x or it.
No. This is the same x that we used above. Okay, so now we'll see the prediction. Now, actually, we have two values. So what will I do here is plt dot scatter. Okay, x comma y pred. See, this is the line it is predicting. I don't know why it's.
See, y equal to mx plus c, when x is 0, so then in your line also, your line will predict y is close to 0 only, right? When mx plus c.
Yeah, but when yeah, exactly, right. Yeah, it's not here actually, it is correct only. Okay, that is the excess, yeah. Right. Because this is here, it always keeps confusing, right? You should take it mod of it. So this is actually your. Right? It is 0.4, right? Got it, right? So see, yeah, I mean, if you rely on graphs and all that, this is where it, but the algorithm gives you the right result, right? So that's what it is. So what it is doing, it is predicting this as a line. You want to plot, so it is finding this is the best line. Okay, now what I should do is I should plot the previous data also so that we can start seeing it. I will make it some other color. Clear or light. Okay, color is equal to red. PLT x comma y. Got it, right? So this red line is the prediction. This blue line is the blue dots are the actual data sets, and this is the your linear regression is finding the best line for you.
I mean, when you say like once you train our model, that means our training is over for this model, right? And now, how could we get the, for example, for certain
New data.
Yeah.
That's what you can use predict. For example, you do this lr.predict and give me some house. In this case, some x. Say,
for example.
Yeah, 1000.
So
See, this is how you will put it actually.
What is 100? What is 100?
100 is one data, 1000 in another data. Each data will be representing like this. Understood, right?
We're not able to see any difference in between 100 square foot and 1000 square foot.
A one digit should be different.
Okay, sorry.
Alright, this is predict. Okay, so given house price, if you try to do the same problem with house price, okay, what will happen is, I mean, for a new house, after you have trained the model, you should give you 6 parameters. Understood, right? And it will tell you the price of the house.
But that graph, can we see
Which one?
that graph?
No, that is 7, 8 dimensional. You cannot plot it. Okay, so cross we cannot see. We can see this 2-dimension thing. So as long as it is 2-dimension, you can find this.
So training the model means like fit, coefficient, intercept, finding all
Change the model means fit.
fit.
Okay, predicting from the trained model is using the function predict.
So what is actually fit doing, sir? Fit
When
is it like in the back end, like it's calculating the best possible line?
yes,
Fit, right?
fit is actually making use of gradient descent to find the best possible line. Okay, so we'll discuss gradient descent in a minute.
So sometimes like people say after a couple of in a certain duration we always need to train our model again and again with new set of data set. Is that like, I mean, if the data set is similar, then we not require anything. If it is only having a different pattern, then we need to predict a new model, or like.
But you cannot conclude this if the data
I mean,
is right.
after all the analysis, we'll say like. Okay,
If the data is changing now and then, like number of people logging into Facebook or whatever, so then you have to train the.
Right. You, I mean, basically you have to update the model.
We have to, yeah.
The hypothesis might change or not? Hypothesis might change. Or not might.
No, it will change. It will change.
I mean,
I mean, if it is not changing, it is good, but possibilities are the reduced.
Yeah.
depends upon different scenarios.
It's like you're connecting where your data coming.
Right,
So
right.
Connecting that, and every day you're updating the model and seeing what is the case.
Right.
So if you see it is deviating, you need to find the other model.
Right, right.
Just you stay with the same model.
They do it in time basis, not like.
No, it's like every day you can see, you can just put a dashboard. Instead of you are taking the data,
This small data.
no, you are taking from some website where the actual user login. You automatically download the data
APIs
and
are
run
there
the model,
to download those.
and you can see the data.
Okay.
But that's a very difficult job. Not so easy to get the data. It's like.
Okay, so what we have now.
It's a data storing somewhere. You can simply SQL query, you can pull in and you can do.
I will do these things in YouTube. You have access on YouTube.
Okay, so yeah, so we have seen some basic case. Now let's come to future listing for that. Okay, so got a hang of this, right? What happened over here? Okay. Now I'll just we have very less time now. We'll just discuss some calculus related things. Okay, so that we can discuss gradient descent forward. You can revise it. Huh? So just understand few important points. See when you, okay, now I'm discussing about gradient descent. Okay, say when you are plotting a graph. Okay, this is a cost function, and this is the say m, right? Considering your line is y is equal to mx. C, for a moment you have made c is equal to 0, is the assumption. Okay, because if you plot c, there is one more dimension. You made c is equal to 0, so you have cost, you have m. Okay, so your cost is a function of only m now, right? Okay, so how many possibilities of m are there? Infinite, right? So for one value of m, the cost is say somewhere here, right? For another value of m, the cost is here. The another value of m cost is here. Another value of m cost is here. Another value of m cost is here. Understood, right? This is the situation. What do you have to do? Yeah. So when you have to reduce the cost, okay, what do you have to do? Where does the cost is least? The bottom point, right? Right. Not necessarily it is touching this. The cost is least at this point. Okay. The cost is least at the point on the slope of the line. You can draw at any point of line, at any point of this curve, you can draw a line.
Yeah.
Right? So at any point we can draw a line. Cost is least where slope is 0. Understood, right? Cost is least where slope is 0. So what is slope of a curve at a point?
Tangent.
So for a curve, what is the equation of this curve? No, I showed it earlier.
Y is equal to mx plus.
No, y is equal to mx plus is a like straight line. What is the equation of this curve? Or for that matter, any curve. I mean, this is I just got it, right?
Square plus b.
No, I showed it earlier. This is the cost function, right?
Okay, it's
This is where I wrote the cost function earlier.
y minus
Y minus y.
hypothesis value.
1 by m
M summation.
I is equal to 1 to m y minus y cap square. This is the cost function, right? For a given x and y, it is plotting this, isn't it? For a given, this m is, remember, not m. This m is slope, huh? Don't get confused here. Okay, so this m is number of points, right? Okay, so if this is the case, okay, if this is the case, what is your y cap? Y cap is your
Y cap is the actual value.
I equal to 1 to
Predicted value.
yeah, y cap is y cap can be replaced by mx, right? I'll change this, I mean, to avoid confusion.
Yeah.
Y cap is right.
K. Just imagine this is K. Okay, K is total number of
Y
points.
cap, where it is intersecting, that is predicted.
Predicted, right. For each point,
I'm mentioning some
I'll do that.
video later.
Yeah.
That is not creating because we are squaring. If you come negative, then
1 by K. K is total number of points. Okay, so y can be replaced by mx. Fine?
C is 0 here.
C is 0, I'll assume, just to simplify it. Okay, so y is equal to mx, you are replacing. Okay. So this was what is this? This is the formula of this curve, right? Given a particular x, it is predicting the cost and you are plotting it. So that means this is the formula of the line. What you have to find now is, given a curve, given a continuous line, this is continuous line. Okay. First point is, what is continuous line? Continuous line means, its derivative is possible, right? And derivative is possible, so it is a continuous line. Okay. You can only find derivative of continuous line. Only find derivative of continuous line. Okay. Now you want to find slope of this continuous line, isn't it? And you want to find that point where the slope is minimal. Slope is 0. Okay. So if you have to find slope at this point, which will be d by d m is slope here, right? And you have this entire line sitting here, right? That will be the slope at there's slopes formula. Given a particular value of x, you can find the slope out here. Right? That is what your calculus does. Calculus means, right? You have a line. Say this is x square line. Huh? This is x square. This is x. This is x square. This is your x square line. So if you have to find slope at one point of time, what will be the slope? This line is x square by d by dx of x square. What is the value? 2x. Right? So the slope at any point of x will be 2x. Right? That is the slope. So now what you have to find? You have to find that point in the curve at which the slope is equal to 0. Okay, that's what. So because when you're trying to plot a tangent here, the slope here is equal to 0. Right? Okay, so you're trying to find a point at which the slope is equal to 0.
There is no change of cost.
There's no change of cost, right? Okay, so I'll have to rub it. Okay, just rewrite the cost function. Cost function is 1 by m by k sigma I is equal to 1 by k, then y minus mx square. Okay, so what you have to do, you have to minimize the cost. And what is the thing that you have to change? You have to minimize the cost, and what is the thing that you have to change? M. Right? So basically, so d by dm, d by dm, you have to change something with respect to this. And what you're doing, 1 by k. Okay, this 1 by k can come up front, right? 1 by k sigma. Okay, all these things can come up front. K I is equal to 1, right? So d by dx of y minus mx whole square. Got it, right? This terms came here earlier. So this, I'll just solve for this part. Okay, d by dm. Okay, how do you replace? You can solve it here itself. Y square plus m square x square, right? Plus, minus 2y mx. Okay, now y will treat this as a constant, isn't it? So this will be gone. Okay, this will be gone. So this part is there, m. So it will become 2m x square, right? Minus 2yx, right? Okay, so if we do this of the center. Okay, so this is what it becomes, and you can take 2x out, so it is yx minus y, isn't it? Yeah, so what do you get here? You get here, so 2x came out and you have mx minus y. So this part, okay, what does it mean? This is your, okay, this is your the descent that will happen. Okay, so just to plot it, I'll redo that. If you're plotting this curve, right, remember this was our curve, right?
Yeah.
You have to find the point at which the cost is minimal. So that is why you're doing d by dx, and you're trying to minimize this. You're trying to minimize the cost, right? So you start with here. This is the line. You will see, at this point of time, you'll see, acha, no, my cost is not at 0. I need to get it to 0. So what is the value by which you'll minimize? You'll minimize with this value. Yeah. Okay.
Yeah,
so this is right. So you will actually minimize by this value. You change your m, and your cost will be reduced by this factor. Okay, so I'll redo this maths part once again. But what is the important part? Don't forget. I mean, just at this point, and just practice this earlier stuff and touch base on a little bit of calculus. Okay, so just do a little bit reading around it so that I can finish this, and I'll do it with complete stuff. I now did it with mx on m only, right? So I have to do it y is equal to mx plus c. This entire formula will calculate the cost, and we'll find the gradient descent maths. Okay, and what is the thing that you're trying to calculate? You're trying to calculate that value of slope. I mean, if you change the slope a bit, how much will your cost change, isn't it? Right? If you find that much number, then it's actually, if you find the relationship between, that's what, right? d by dx and x square, it is 2x. You mean, what does it mean? If you change y is equal to x square, right? If you change x by one value, y will change by 2x times. That's what it means, right? So if you want to reduce a value of x square, you'll reduce x by 1, isn't it? Okay, that's what we're trying to do. That's what gradient descent is. You try to find the relationship between the one of the m and c with respect to the cost, so that you can change the m. Okay, if I increase m by 1, cost will be increased by 10. So I should be decreasing m by 1 in case I want to reduce the cost. At the same time, I can do, you have to, like, many times you play those games, right? Yeah, you have to change this, which is the best value. This is what your gradient descent does, actually. Understood the physical meaning of gradient descent?
Yeah.
Okay.
So is it done like always by adjusting the slope?
Yeah, always by adjusting the slope and intercept. This is only for 2 dimension. Gradient descent is capable of doing this in n dimension. Okay, and this is the I mean, when you do differentiation of it, this is the value that you might use different maths. I will show some other maths of the thing, but understood that meaning, right? That is what is important. Okay, by what value should you be changing the slope so that your cost reduces, so that you don't have to pre-calculate all the values, right? What we discussed earlier, that it will calculate for all of them, but actually that is not possible, right? That is where your gradient descent comes into picture.
However, if you do for alternate points to calculate the initial cost function, if you alternate point, it will calculate the cost function.
No, it will not need to calculate cost now. It has the function, right?
Yeah.
It has the function. Okay, so using this maths, it will find out that d by dm is equal to something like it is like 2x into mx minus y. Okay, so yeah, so here, yeah, so here it realizes. I think there's something I have to change here. So here it realizes.
To start with that, x1 10x's. To start with every alternate point, it will calculate the m, then it will try to reduce the cost function. That's what the algorithm will do. But is that the way it is doing, right?
No, I think we to try to when we calculate them definitely we might go the wrong way.
It's correct.
Machine
Just okay. So yeah. So yeah, it's correct only. No matter how you're doing, so you're getting this. Okay. So you see, what is this? If you change the value of x by some value, this is m by some value. This is how the value of cost function will change. Okay. So this is what I did in I solved the differential calculus this method, like a minus a plus b whole square, a square plus b square plus 2a. I solved it in different way also, where 2 came first, y minus mx, then this I'm doing d by dx of this. So both the ways I'm getting the same difference. Okay. Got it?
So
Okay.
now you say like the cost will be decreasing by 2x of mx minus y.
If you change m by one value, the actual cost will be
decreases by that
that
total
value. Right. Decreases, increases by that value.
Okay, so if I change the if I change the slope like positively or negatively, like, it is directly proportional, right?
Yeah.
So if I in this case, yeah.
So if in this case,
different m also, like 1 by m.
So assume you are at this point, right? This point, but where you should be moving, you should be moving towards this direction, right?
Yeah.
Okay, so this will be the slope of the line. So it means you will be moving this direction. Say you are here. The slope of the line is this guy. So you're moving in this direction. This will moving in that direction. So effectively, what you have to find, your graphs can be something like this, right? You have to find, you have to try moving in from here and somehow reach here, somehow reach here, somehow reach here. Okay, so just do a little bit of reading around it. Okay, the syntax might be changing from book to book, stuff to stuff, but core concepts remain the same.
What is that book?
So do that. So you can read any of this. PDF is there, but you can Google the names of it. Machine learning, Tom Mitchell, that is one book. Then this is another good book. Where is it? ESLII. No, I will show the author's name.
Small number of different producers, but huge number.
That's why that it will go for alternate points only, right? Anything. Need to do assigning order to complete.
Yeah.
You might be having the recordings for this batch, right? The previous sessions of this batch. Can you share the
It's recording. Okay, I'll share. I would need email IDs for actually.
No, that was last.
This is not sure.
Sunday session is last.
So You see?
Yes.
No, I think I have to ask my question. Your Python batch is over or what?
One more class.
I think it's tomorrow.
For us, it's tomorrow, right?
Okay, so let me stop recording.
You also have.
I'm ending the meeting, guys.
And the tomorrow class is there.
No, tomorrow. No, it's on Wednesday.
So I need the recording.
Recording, yeah, I'll sit on it today. Okay.
It will be Monday, Wednesday,
Monday, Wednesday, and Friday.
Friday. So if you could please share this by today, then.
Wait, I'll do that now. So.
Today is